Today we're going to talk about the free body diagram and its use in solving problems in statics. We can use the force and moment balance equations to solve for unknown forces and moments in terms of applied forces and moments when the system is rigid and in static equilibrium, provided that the problem is statically determinate. Now, real systems in biomechanics are often not statically determinate. There are usually more unknowns than we can solve for with the equations of statics alone, but we can often make simplifying assumptions to render the system statically determinate. As we also saw, sometimes systems that appear to be static, in fact, are not static, they're unstable. But having determined that a system is statically determinate, we need a way of formulating and solving the problem. So the general approach to solving a problem in statics goes as follows. First, we sketch the physical system, labeling the known geometric positions and angles and drawing the applied force vectors and moments, including their lines of action or axes of rotation, respectively. Next, we state what is given or known and identify what values are unknown and need to be found or solved for. The third step is to draw a free body diagram by considering a point in the system and exposing all of the forces or moments acting at that point, including any reaction forces and moments arising from Newton's third law. And so sometimes this involves making an imaginary cut in structures or members to expose conceptually that reaction force. So at this point, we are ready to establish whether the problem is in fact statically determinate. If it's not, then we have to revise the free body diagram or the problem statement, for example, by identifying additional knowns or simplifying the system to reduce the number of unknowns, in which case we might have to make simplifying assumptions that we need to state clearly. We should take care to include a coordinate system in your diagram so you know which direction represents the x-axis and which direction represents the y and z-axes. Next, we write down the governing equations. So the sum of the external forces balances to 0, the sum of the moments balances to 0. And then we use those equations to solve for the unknowns, being careful to show all your working. Clearly highlight your answers for the unknown quantities and remember to provide proper units and to use an appropriate number of significant figures. Finally, check to make sure that your solutions, in particular the signs of your solutions, the directions of the forces that you've solved for, make intuitive physical sense. So let's do a simple example that we can complete in class. So here's a wall with a pin-jointed structure. We have at A and B connections of the structure to the wall. The structure connecting A to C is a rod. And then we have a cable connecting B to C. Then an external force is applied at C with a load of 400 newtons. Now the orientation of the structures are given, so the angle between the cable and the wall is 50 degrees, the angle between the rod and the wall is 35 degrees, and the angle between the load and the vertical is 25 degrees. Now, It's worth pointing out the difference between a cable and a rod here. A cable can support load and tension, but not compression. As you know, a cable or a rope will buckle under compression. So the force in that cable will be positive and can be supported if the cable is pulling against the load. But if the load is pushing on the cable, then the cable can't resist it. The rod, on the other hand, can support a compression. So let's draw our free body diagram centered on C. So by making a cut in the cable, we expose a force here. And by making a cut in the rod, we expose a force here. We'll label the force in the cable FBC, the force in the rod FAC, and then the external load is F. We know the angles, and this is a 2D problem, so there are no forces with Z components and no moments with X or Y components. Now, since this whole system is pin-jointed, as in our examples of statically determinate structures before, all the net moments will be zero, and therefore they will already be in balance, and therefore there are no moments to solve for, and we can't make use of the moment equations. So what do we know? Well, we know the force vector F, and we have both 2D components of the force vector, since we have its magnitude of 400 newtons and the angle that it makes to the vertical axis. We also know the angle of the force BC and the angle of the force AC. What we don't know is the magnitude of the force BC or the magnitude of the force AC. So is the problem statically determinate? So is this problem statically determinate? Well, there are no unknown moments and no moment equations to use in this problem because it's a pin-jointed structure, so none of the intersections can support a net moment. So that means we're left with two force balance equations. One saying the sum of the x forces is zero, and the other saying the sum of the y component of the forces is zero. And we have two unknowns, the magnitude of the force FAB and the magnitude of the force FBC. And so therefore, yes, it appears that the problem is statically determinate. But there is one caveat here that we should consider. Remember that force BC is in a cable. So if the force is pulling away from the wall and down, then this cable will be in tension and the structure will be stable. If, on the other hand, the applied force was pushing up or to the left, you can see that the cable would not be able to bear any force to maintain equilibrium of C, and the structure would start to rotate and collapse, and so it actually wouldn't be statically determinate. Conversely, if this structure was the rod and this structure was the cable, then with the loads as we've had them, again, the structure would not be stable. So yes, the structure is statically determinate, but we can't just add up knowns and unknowns. We also need to consider the physics of the situation. So why don't you go ahead, now that we've stated the assumptions of this problem, and see if you can solve it and see what answer you get, and then we'll talk about it in class. Did you get that the force in the cable FBC has a magnitude of 348 newtons, or perhaps you wrote 350, and the force in the rod the magnitude of the force in the rod is 170 newtons? If so, I think you probably did it correctly. See you next time.